In 1905, a 26-year-old young physicist, you can see him here, single-handedly changed the flow of physics. You already know who this scientist or who this physicist is. He's well known Albert Einstein. The theory that he explained was the special theory of relativity. Hang on, physics lovers. I'm going to explain this formidable theory step by step from today onwards. Welcome to Genius Physics with Chamila. Special relativity is a very wide area in physics, guys, as it affects every single aspect in physics. Therefore, for better understanding, I'll split this lesson into few parts. So this is going to be the very first part of this lesson. In this very first part, I'm going to discuss these topics. Very first topic will be the postulates of special relativity. So there are major two postulates. I'm going to introduce what these two postulates are. The second part of the lesson will be, if you don't know what the inertial reference frames are yet, it will be a bit hard for you to grasp this concept. So therefore, I'm going to introduce and I'm going to teach you what the inertial reference frames are, the nature of inertial reference frames. I'm going to introduce. The third part of the lesson will be the most important part. The third part will be the time dilation. Depending on the reference frame that you are observing stuff, the time varies. This is the most important thing. In Newtonian physics, guys, back then the people had believed that the time is absolute, it doesn't change. That's what their belief was. Is time really an absolute thing? Can the 1 second felt by ourselves be equal to 1 second felt by somewhere else in the universe? Can the magnitude of 1 hour be same to the 1 hour magnitude of 1 hour in somewhere else in the universe? Is the Newton correct? Because according to Newton's arguments, the time is something absolute. You can't change the magnitude of the time. 1 second is 1 second itself. This is what Newton said. But Albert Einstein didn't agree with that anymore. He said that what he observed was, he realized that the speed of light is constant in every inertial reference frame. This is the breakthrough in physics. So as a result of that, he felt that and he realized that the time cannot be absolute. I will explain this properly with the postulates of special relativity, guys. Hang on. But if you really want to understand the postulates of special relativity, there is something that you really need to know in advance. So you need to know what the inertial reference frames are properly. I'm going to introduce and I'm going to explain what the inertial reference frames are. Take a look at this image. So there's a person sitting in the car. There's a tree next to him and he sees that the tree is at rest. Then that's totally fine because the person is at rest, the car itself is at rest, the reference frame of the person is now car, the car is at rest, so therefore he sees that the tree is at rest. But imagine for a moment the second video clip. Just take a look at the second video clip. When the car starts to move in forward direction, the person doesn't feel that the car is moving at all, because look at, if you want to understand this concept, just take a look at, or just look around you. The stuff, most of the stuff around you are at rest with respect to yourself and with respect to the earth. As a result of that, we don't even feel that they are moving. But in reality, all of us are moving along with the earth, but we don't even feel that. Right. So now imagine for a moment if this car is moving at a constant velocity, but he doesn't feel that he's moving at constant velocity as he's sitting in the car, but he feels that the tree is moving in backward velocity, backward direction at a constant velocity. This is acceptable. I'll tell you why later on. But imagine when the car starts to accelerate. Now, he's in a hurry, he's going to accelerate the vehicle. As he starts to accelerate, he doesn't feel that he is accelerating. What he feels is the tree is accelerating in backward direction with respect to himself. This is the point where the problem arises. Because can this be true? According to Newton's second law, we already know that if anything has to accelerate, there must be a force on it. Not just a force, it should be a resultant force. There must be resultant force on it to accelerate that object. But now this is a weird observation, because as the person sees that the tree is accelerating in backward direction without even having a resultant force on the tree. He cannot agree with this anymore. So these sort of frames actually, the Newton's laws are not valid in these sort of frames. So these frames are called the non-inertial frames. But the previous two reference frames, the vehicle is at rest, the resting moment, and when the vehicle was moving at constant velocity, at these two different occasions, the observations were totally acceptable, because as the person observes, the tree was at rest, totally fine. There was no resultant force on it. Therefore, the tree is at rest. It doesn't violate the Newton's second law. And as during the second observation, he sees that the tree is moving at a constant velocity in backward direction. Still, it is applicable. It is valid, as there is no net resultant force on the tree. So these sort of reference frames are called the inertial frames. Let's quickly go through the postulates of special relativity. The first postulate is the laws of physics are the same in every inertial reference frame. The second postulate is the speed of light is same for the every inertial reference frame. Based on these two postulates, we can derive so many stuff based on physics, but my today's priority is this time dilation. So I'm going to explain and prove the time dilation using these two postulates. Right. Now, the second postulate is very important out of these two postulates. So what does it try to say? The speed of light is constant in every reference frame. Right. Now quickly take a look at these. Can you see, guys, in this video, there are two observers, and these two observers are observing the light coming from two light sources. The first light source is at rest, and the light coming from the first light source is observed by the observer number 1. In the meanwhile, the observer number 2 is observing the light coming from the light source number 2. But this light source number 2 is not at rest. It is coming towards the observer number 2 at 10,000 meters per second. After observing these lights which are coming towards these observers, they're having a conversation. In the second part of the video, you can see that they're having a conversation. Can you see in this conversation that observer number 1 is saying that the speed of light as observed by the observer number 1 is 3 times 10 to the power 8. But we already know that the speed of light is 3 times 10 to the power 8. So that's a standard value. That's a constant standard value. Doesn't matter. But look at what the observer number 2 is saying here. As observed by the observer number 2, still the speed of light is 3 times 10 to the power 8 meters per second. But surprisingly, this is the same value. Does it violate the relative motion concepts that we have already learned? The problem is we already know that according to the relative motion, when something is coming towards you, in the meantime, if it is emitting something, or for example, sound waves, the speed of that sound wave is supposed to be the addition of or the summation of the speed itself plus the speed of the source. But surprisingly here, still the speed is not 3 times 10 to the power 8 meters per second plus 10,000 meters per second. It has completely changed, and this value is now 3 times 10 to the power 8 meters per second. This is the most important breakthrough that Albert Einstein came across, because he realized that experimentally this has been proved, guys. So there are so many proofs. Later on in my next videos, I'm going to show you the provings, right? But not today. This is the most important part of this video. So then this clearly shows that the speed of light is constant for every observer in every inertial reference frame. So based on this, we can derive the time dilation as shown in my next video, right? So now look at this part of this video. This is interesting. Now, as you see here, there's a football. It continuously collides with the upper part of there's a wall which is at rest. It's continuously colliding with the upper part of the wall and the lower part of the wall, right? So now imagine a stationary observer. Now we all are stationary observers. Up to some extent it's correct, because with respect to us, all of those things are at rest, but up to some extent this is correct because Earth is moving. So with respect to Earth, we are at rest. So as all of us observe, the time it takes to reach, or time it takes to travel in between these walls, the first wall and the second wall, let me take the time is simple t. If that time is simple t, and now in my second part of this video, the second part of this animation, can you see that the walls are moving? They are no longer at rest. The walls are moving, but still the football is continuously colliding with the upper part of the wall and the lower part of the wall, right? So now when you observe the same thing, now let me take, now this is no longer a football. So this is the most important part. So instead of a football, we are going to replace light waves. So now this is a light wave. It is no longer a football. Now if it is a light wave, now it's continuously colliding with the walls, and the observer, if there's an observer who's there in between these walls, now just you can imagine it. You can go and sit there within these walls, and you can observe this same light, but you won't ever feel the motion of these walls. What you will observe is just, as we observed previously, you will observe the motion of the ball, but not the motion of the walls. The ball is not the ball anymore. No, don't forget that. Now it's just light. It's a light wave. So now, but as stationary observers, but still we are at rest, right? But the walls are moving. But we observe a zigzag motion. The ball is no longer moving in a straight path. as we observe, this is a zigzag motion. So based on this observation, I'm going to conclude and I'm going to derive a relationship to show you the time dilation. Let's quickly get back to the mathematical concepts and I'm going to show you how this time dilation works. Let's get started with the two walls that we met earlier. So these are the two walls now, and this is the football which is moving in between these two walls, and it is no longer a football. As I mentioned earlier, now it's a light wave. Now instead of a football, we replace a light wave, as it's much easier for us to analyze this with the football. I put a football here, right? But now, this is my stationary observer. As he observes, it's not a very complicated motion. This football or the light wave is moving at speed of light, and it is moving in between these two walls, and hits the first wall, which means my B wall, and this is my A wall, and it reaches the A wall again. Let me take the time it takes, time the ball takes, ball, or if you want you can replace the light wave, ball or the light wave as you wish. Light wave takes the time the ball takes to reach the wall number A once again, right? That is T naught, right? Let me take the time as T naught, right? So that now in terms of the L naught, now the distance between these two walls, let me take that distance as L naught, guys. And we already know the speed of light. We usually use c to represent speed of light. I'm not going to deal with numbers, as I'm going to make as I'm going to derive an equation here. I'm not going to deal with numbers here, but anyway, the distance between these two walls is L naught now, and the speed of light is simple v. So under this circumstance, I can write an expression for T naught in terms of L naught and C, because the total distance traveled by the light wave during its motion is now 2L. And 2L over, and the speed of light is C, right? So now it is 2L over C, and I label this equation as my first equation, and I keep it aside for a while until I get back to the same equation again. Right, now my second case. Now this is my moving frame, and these two walls are no longer at rest with respect to the observer, and now this is moving, and imagine this is the as it's moving, I took some snapshots. This is my very first moment, and after some time, some time, I'm not going to use the time yet. After some time it is somewhere here, and after some time it is somewhere here. It is like that, it is moving. So if the speed of this frame is simple v, if the speed of this frame is simple v, now, so this is my light wave again, and I'm not going to draw few frames. It's a bit hard for us to understand, right? So therefore I'm going to deal with the same frame without drawing few frames, but you should be smart enough to recognize that this is still not the same frame. Now it is moving few moments. Right, now it's following a zigzag path. It's no longer a vertical path. It's a zigzag path like this, right, here and there. Now right, but this distance is still L naught, and what I'm going to do here is I'm going to take the time now it takes to complete, or it takes to reach the wall number A. So this is still the wall number A, and this is my wall number V. So the time taken to reach the wall number A is simple t with respect to the observer who's observing uh, externally, and he's at rest, and this guy, right? So now this time, the time taken to reach the wall A once again with respective to our observer, the stationary observer. Yeah, now it is simple t, so I'm going to take it as simple t now. Right, now during this time, guys, we can understand. Now I'm going to use this triangle, which is, I'm going to label this triangle. Even though I have this trajectory, I'm not going to use that trajectory or that path. So my triangle is, now I'm going to label this triangle PQR. I'm going to consider this PQR triangle now. Right now, the this distance, actually we can find this distance, guys, because here to there the time taken to travel from here to there is total time from P to this uh, let me take this as the R point. So the P to R point, the total time it takes to travel from P to R is T, but the time it takes to travel from P to Q is T over 2, right? So then let me take the time as T over 2, right? And the second important thing is uh, here to there. Now here I have L naught and T naught over 2, and the total distance traveled by, and here to there distance, because the time from here to there P to Q is now T over 2. Therefore the PR distance is, guys, that's still the speed is the speed of light. We already know that the speed of light does not depend on the motion of the reference frame, which means the inertial reference frame. So therefore this distance, the PR distance, is supposed to be CT over 2. That is CT over 2. That's very important. Right, now I'm going to use very important and one of the popular relationships, which is, you guys already know what this relationship is, which is Pythagoras theorem. So according to Pythagoras theorem, now I can which color should I use? Yeah, red color. So according to Pythagoras theorem, now I can show that the PQ squared plus QR squared is equal to PR squared. So that the PQ squared is now, right, the PQ. Now the speed of the plane is V, so therefore this distance, the PQ distance, is VT over 2, because VT over 2, that's the total distance. I mean, the distance between PQ. So therefore the PQ now is VT over 2 and the total squared, plus QR squared is uh, L naught squared is equal to PR squared is, now you can write that the CT over 2 squared, total complete squared, right? Yeah, now so this is now V squared T squared over 4 plus L naught squared plus, oh sorry, my bad, is equal to C squared T squared over 4, right? Right, now let me take this equation onto other side, not equation, this term onto other side. So L naught squared is now is equal to C squared T squared over 4 minus V squared T squared over 4. Right, furthermore, now we can take L naught squared and T naught squared over 4 and here within bracket c squared minus v squared. That's fine. So now why can't I substitute t? Now t squared is equal to 4L naught squared over c squared minus v squared. That's fine. Right, now I shouldn't forget the equation that we have already derived previously, so which is 2L, the T naught. T naught is equal to here 2L, oh L naught, my bad, L naught, 2L naught over C, 2L naught over C relationship. So I'm going to use the same relationship now. So T squared, I keep it. Oh, I'm just going to use white color, it doesn't matter, right? The 4L naught squared, and I'm going to divide the denominator and numerator by c squared. C squared over here now c squared over c squared minus v squared over c squared. Right, now I can see that the t squared is equal to 4L naught squared over here 1 minus v squared over c squared. That's a little mistake I made. A little blunder, doesn't matter. The t squared is now equal to 4L naught squared over c squared, but here 1 minus v squared over c squared. But here I should never forget that the L naught over c, or here 2L naught over c actually, is equal to t naught as we derived earlier. So now 2L naught over c. So why can't I now substitute these values? Now I can say that t squared is equal here. This is 2L naught over c complete squared, guys. 1 minus v squared over c squared. So I can do it over here. Now I can see that t squared is equal. Now this is my t naught squared over 1 minus v squared over c squared. Right. It's almost over now. So now t is therefore is equal to t naught squared over 1 minus v squared over c squared, and when I put the square root of this, the t naught square to square root, you can cancel out that 2, and the only final remaining equation is, I'm going to use a different color to show as it's very important here. The t is equal to now t naught over 1 minus v squared over c squared complete squared. Right, now guys, this is very important. So even if this is moving, now let me draw the same moving frame again. So this is my moving frame V, and imagine there's a person here sitting in between these two walls, right? And this is my person A, not A this time. Let me take the person here, X person, and this is my Y person. Now the as X person observes, he doesn't know that the frame is moving. Only thing that he observes is this is what person X observes. He just sees the vertical motion, and the time that which is measured by the person X is t naught, right? The time measured by the person X is t naught, but to hit the wall A, and here wall B, but to hit the wall A, to reach the wall A again, according to or the from the point of view of the X, right, that the time taken is t naught. But with respect to the observer Y, right, the time taken to reach the wall again, the wall capital A again, is capital T, not capital T, simple T, right? So now this is very important. Therefore now this clearly shows that the time experienced by the X person is t naught, while the same time measured by the person Y is simple T. Now, as you can see here, the same equation again I write again. So t is equal t naught 1 minus v squared over c squared and the square root of this. Now, uh, when v has a value, you can clearly see that this one is 1 minus v squared over c squared and this root. This one is definitely, because there's a subtraction, v squared minus c squared is subtracting from the 1, so therefore this is definitely less than 1. This is definitely less than 1, right? So therefore you can clearly see that the t will always, because now denominator you divide, this denominator is not 1, it is something less than 1. So as the denominator is less than 1, it is always, this t is always greater than t naught, which means now the time experienced by the person who's in the moving frame, even though it is t naught, right? So that time is experienced by the same person. That time is now, for example, I imagine 1 minute for this x, the person x, the 1 minute or 1 hour as you wish. So let me argue it with 1 minute. So 1 minute for this person, he feels that time, which means the x person x feels that time as 1 minute, but the for the person y, this time is something longer than 1 minute. 1 minute, right? So which means now uh, for x person, when he spends 10 years, the person y spends the time is something greater for that person, right? So then person y experiences sometimes of 15 years. I don't know, I'm just telling, my bad, 15 years. It depends on the speed of the person, so speed of his frame. So therefore this clearly shows that when you are moving with respect to something else, you experience a slow kind of a slower time. This time, the speed of the time is a bit slower for the person who's there in the moving frame, while the other person who's there in the rest frame, but no one is at rest, everyone is moving with respect to something else. But when you compare the motion, when someone is moving relative to something else, now the time taken by that person, so time it takes, the time taken by the person who's at the rest frame will be something or somewhat greater than the other person, right? So that is it, guys. Hope you guys have enjoyed the video. Goodbye until we meet with the next episode of Special Relativity. Thank you.